Hello, welcome to our webinar, Overview of 61010-1 3rd edition. Thank you for joining us today. This webinar is being given by MET Laboratories. MET is a leader in the testing of electrical and electronic equipment for environmental hardiness, product safety, and electromagnetic compatibility. MET operates world-class labs in Baltimore, Maryland, Santa Clara and Union City, California, Austin, Texas, and also runs operations in China, Taiwan, Korea, and Italy. This webinar will run 30 to 45 minutes with an additional 15 minutes for questions and answers. Due to the number of registrants, all attendees will have their phones muted. If you have a question, please type it in the questions area of your control panel. We will attempt to answer all questions at the end. If you're having technical difficulties, you can contact us the same way, or if you can't, call us at 410-935-6053. 410-935-6053. Just a quick note on other upcoming events. In 2 weeks, MET is giving another free webinar on HALT testing effectively. And then in September, MET is hosting our annual Global Compliance Seminar and Crab Feast in Baltimore. You can register for these events at www.metlabs.com. Today's webinar is being presented by Lauren Foster. Lauren is a MET Senior Product Safety Engineer. At this point, I will hand over the presentation to Lauren.
Hello, I'm Lauren. I'm one of the Senior Project Engineers here at MET Labs. Today I want to talk about 61010-1 and the changes that have come about with the 3rd edition. If you're not familiar with MET Laboratories, I want to tell you a few things about us. We've been doing product safety for over 50 years. We're approved to investigate to over 200 different standards for North American, European, and international markets. In addition to performing safety testing, we're also equipped to perform testing for EMI, ESD, environmental safety, and NEBS. In today's presentation, I'd like to start with some basics about the 61010 standard and then go into the requirements for the 3rd edition. The types of products that are covered in the standard involve test, process control, and lab equipment. There are 8 basic types of hazards that the standard investigates a product to. In addition to the most obvious hazards, the standard also includes an examination of hazards related to fluid and pressure, radiation, and explosion. This list is meant to be all-inclusive, but it may not include hazards that arise from new technologies, and you will find that the 3rd edition standard takes this into account. When you're designing a product to meet the standard, there are some basic things you can look at. To manage shock and energy, you will need to use components that are designed to step down voltage to suitable levels. You will need to manage the shape and material of your enclosure and the way handles and mounting brackets are designed so they can handle the weight. You can also manage the possibility of fire with overcurrent devices as well as properly flame-rated components. Managing the heat of the product can be done with small holes or fins for ventilations and fans where necessary. Pressure systems may need overpressure devices or must simply withstand the pressure that can build up in the system. Radiation should be either reduced or contained or managed with an interlock so that it's only on when necessary. Battery safety also needs to be managed to prevent reverse charging, excessive discharge, since even certified lithium batteries can explode. Again, I want to reiterate the cruciality of enclosure design. Using certified components ensures that they will always meet a given standard, even if the manufacturer makes a design change that you can't control. If you don't use a certified component, you run the risk of having it fail during safety testing, and even if it passes, it may need to be tested every year or more, and that can get expensive. Using the component within its ratings also ensures that it won't overheat or break down under the conditions of your product. If you choose to use a component outside of its ratings, we have to treat it as an uncertified component with extra testing, and if it passes, annual inspections. Board layout is critical when you have both hazardous and low voltage components on the same board. If you have limited space, you may need to use a certified conformal coating or put slits in the board in order to meet the spacing requirements. Creepage as the bug crawls, clearance as the crow flies. I wanted to make sure you knew what tests we'll be performing on your product. We're examining the product in terms of the 8 types of hazards I mentioned earlier, grouped as follows: shock hazards, mechanical hazards, excessive temperature, fluids, radiation and sound, explosion from batteries, and any combination of hazards caused by circuit or component faults. This is in addition to the overall review and inspection of the product and its components. I also want to note that testing is only one of the aspects of our investigation of your product. We typically do it after we've reviewed the product, since it can be destructive. I'm now going to switch gears and talk specifically about the 3rd edition standards. As you can see, all major bodies have now switched over to the 3rd edition for new products, and eventually 2nd edition will become obsolete and old products will need to be converted. The conversion date for Europe in EN 61010-1 is later this year. The conversion date for US and Canada is in 2018. So now let's talk about actual changes to the standards, starting with the scope. The new standard includes products up to 1,000 volts, includes professional and non-professional products, hazards to service personnel as well as operators, and includes new classes of meters. Some products have been removed from the scope, and last, power supplies and computer equipment are only included if they are part of the equipment that falls under the scope of the standard. There have been some changes to the marking and documentation requirements. There's a new radiation hazard symbol. There's a new protocol for marking emergency stops for urgent action or warning of danger. And there's a requirement that emergency stops have a secondary means of alert or indication if there's potential for harm to a person or the environment instead of just a need for urgent action. Now, here are 6 new requirements to the user manual. You'll need to provide information on how to avoid a hazard that can't be eliminated in the design. You'll need a statement to only use manufacturer-approved accessories, such as probes. You'll need to provide information on how to tell if a measuring device, such as a hazardous gas sensor, is malfunctioning. You'll need a statement not to use inappropriately rated power cords. You'll need information on any hazards from putting the product into an unusual environment, such as a wet or damp location, high humidity, or a toxic environment. And you'll need information on any hazards that may occur when the equipment is integrated into a larger system. Now let's talk about changes to the standard in electric shock design and testing. There are 4 major changes to how the 3rd edition addresses electric shock. First, the way that you can protect an accessible part from electric shock has been expanded. Next, the bonding impedance test has changed drastically for North American products. The creepage and clearance requirements have been greatly expanded, and the dielectric strength test requirements have become more severe. I want to review means of protection. All accessible parts must have two means of protection against electric shock hazards, so that even though a hazardous voltage, say 120 to 40 volts, is coming into the product, a low voltage, such as 30 VRMS or 60 VDC, is all that you can touch, even if there's a fault in the equipment. The most obvious primary form of protection is the enclosure. The most common primary protection is basic insulation, such as what you have between a transformer or optocoupler, or even space. You can also use protective impedance or series resistance. Now, if one of those fails, you have to have an additional form of protection. The most common additional form of protection is metal enclosure and bonding. For plastic enclosures, it's supplementary insulation, which together with basic insulation forms double insulation. Another method is disconnection from the supply. Now, if you want, you can use one form of protection by itself. If it is either reinforced insulation, which would have twice the insulation as basic, or protective impedance that steps down the voltage and current and also provides insulation. The third edition has now added a fourth means of secondary protection, a voltage or current limiting device which together with the primary protection can protect accessible parts from hazardous voltage. Here are the voltage and current limits that a limiting device must meet. They're spelled out more completely in Clause 6.3.2 of the standard. Voltage limiting devices must reduce the voltage to less than 30 VRMS or 60 VDC for North America. Current limiting devices must reduce the current to less than 0.5 milliamps RMS or 2 milliamps DC. There are also component selection and layout requirements when using current or voltage limiting devices. The ratings of each limiting device must be sufficient for the voltage and current. The spacings on the board for each component must meet creepage and clearance values for supplementary insulation. If you use resistors in series or any other type of protective impedance as your means of protecting accessible parts from shock hazards, there are new design and component selection criteria which are pretty much the same as those for a single current or voltage limiting device that I mentioned in the previous slide. First, the final voltage or current must be at or below the electric shock safety limits for voltage or current for accessible parts. Next, the ratings of each component must be sufficient for the voltage and power. Last, the spacings on the board for each component must meet creepage and clearance requirements for basic insulation or reinforced insulation if a single component is used. Next, there are some changes to the bonding impedance test. The first change is that the new limit for non-detachable cords, instead of 100 milliohms, is now 200 milliohms. Again, this is for non-detachable cords. And it's tested from the end of the cord to any point on the enclosure which is accessible. Although the bonding impedance test conditions and limits for Europe have not changed, the North American test is significantly more severe. Instead of starting at a 25 amp current, in North America, the test now requires 40 amps, 2 times the trip current of most breakers. Instead of a limit of 0.1 ohms, the limit is now in terms of voltage and may be less than 0.1 ohms if the test current is higher. And instead of 1 minute, in North America, the test requires at least 2 minutes mimicking the time lapse of tripping the breaker, and increases based on the value of the overcurrent protection. There's also a new test for transformer protective bonding screens. The limit of either 0.1 ohm or 10 VAC between bonding screen and earthing terminal. A specially prepared transformer is used with a lead wire from the free end of the screen to make sure that the entire screen is part of the test circuit. One of the biggest changes in the standard is the means of determining which creepage and clearance values to apply. Since the limits are based on the overvoltage category, I wanted to review those terms first. An overvoltage category 1 product must be connected to a source that is protected from overvoltage transients. 61010-1 does not cover these products. An overvoltage category 2 product does not assume such overvoltage protection. Under the environmental conditions in the second edition, overvoltage category 2 was assumed. This means that a 61010 second edition part was only meant for products which were protected by a breaker panel. The third edition expands the scope to include products which are Category 3, i.e. parts of the building installation on the supply side of a breaker, and Category 4, equipment that's installed at the origin of the electrical supply to a building, such as electricity meters. Since the majority of products fall under overvoltage Category 2, and under 300 volts, these are the focus of the body of the 61010-1 standard. However, for products between 300 and 1,000 volts, or used in Category 3 or 4 installations, the third edition standard has a new Annex K, which gives creepages and clearance and dielectric strength values for those cases. Similarly, the limits for products covered in the standard have gone from 600 to 1,000 volts. This doesn't affect most North American or European products. One more change to creepage and clearance. There is now a required spacing between line and neutral on the supply side of an overcurrent protective device based on basic insulation. The values are based on North American and European products and are given here. Another change in the standard is the inclusion of spacings in solid insulation, specifically molded and potted parts, multi-layer circuit boards, and thin film. The standard addresses distance between traces within a layer, L, and distance between layers, C. For products under 300 volts, there's a separation requirement of 0.4 millimeters for both L and C, whether the insulation is basic, double, or reinforced. Between layers of circuit boards, there's also the option of doing a dielectric strength test instead of a measurement. For thin films, the separation between conductors on the same layer is the same as clearance values in air, but between layers it is treated the same as a circuit board. Insulation tape is treated as a thin film. However, since it's almost always less than 0.4 millimeters, dielectric strength testing is required. Another big change is the dielectric strength requirements. In the second edition standard, dielectric strength values were based on the clearance value. They are now based on the rated or working voltage. This does not constitute a major change for manufacturers, but it does simplify things when interpreting the standard. The test conditions have also changed for third edition. They are significantly higher and for longer durations than for second edition. For most North American products used on a 120-volt line, the voltage for basic insulation has increased from 840 VAC to 1350 VAC. The voltage for reinforced insulation has changed from 1,344 VAC to 2,700 VAC. This is higher than the 2,000-volt requirement in 6950-1. Also, the duration of both AC and DC tests has increased from 5 seconds to 1 minute. For most European products used on a 220 to 240 volt line, the voltage for basic insulation has increased from 1390 volts to 1500 volts. The voltage for reinforced insulation has increased from 2,224 volts to 3,000 volts. This is the same as the requirement for 6950-1. Again, the duration of both AC and DC tests has increased from 5 seconds to 1 minute. Again, the same as the duration for 6950-1. However, dielectric strength tests on secondary circuits, the duration is still only 5 seconds. In Annex K, for products above 300 volts or above overvoltage category 2, 2 tests are now required, a 5-second test and a 1-minute test. The reason for doing both tests is because the first checks the effects of transient overvoltages, while the second checks the effects of long-term stress of solid insulation. If doing AC tests only the 1-minute test needs to be done. Now, luckily for routine testing, the values for dielectric strength testing are primarily the same. For 120-volt products, the values are identical. For 220 to 240-volt products, the numbers have been rounded up slightly from 1390 to 1400 VAC and from 1970 to 2000 VDC. The ramp time for AC and DC testing has been expanded to 5 seconds, which is less severe. The duration is still 2 seconds. Also in 3rd edition, an exception has been made for products with voltage-limiting devices such as VDRs, bridging basic insulation between line and ground. The production line dielectric strength test voltage can be lowered. If you have such a component, you need to determine the working voltage for your power supply that must be used to determine the minimum voltage. This can be higher than the rated voltage because it is the voltage across the transformer, and this can be stepped up with a switch mode power supply to as much as 900 volts peak. If the working voltage is higher than the voltage limit of your limiting device, or VDR, you need to get a component with a higher limit or remove the component during testing. I'd like to make note of an interesting definition in 61010-1. If you're familiar with 6950-1, you may have heard the term SELV, or Safety Extra Low Voltage Circuit. This is not defined in 61010-1. Instead, 61010-1 uses the terms secondary circuit and accessible part. They're not the same. A secondary circuit is only a circuit which is separated from mains by an isolating transformer with reinforced insulation or a protective grounded screen. Because the transformer protects secondary from transients, secondary circuits can have lower creepages, clearances, solid insulation thicknesses, and dielectric strength values. A secondary circuit is not necessarily low voltage and does not have to be. In contrast, an accessible part does not have to be separated from mains by reinforced insulation, such as a transformer. It can be separated by another component or protective impedance or some form of basic insulation, but it has to be either low voltage or low current, low capacitance. Second edition did not define secondary circuits, although they were frequently referenced. So this change is just a clarification. It does not affect any tests or any other requirements in the standard. Now let's talk about changes in mechanical hazard design and testing. 6.10.10 third edition defines 5 types of mechanical hazards. Some of the requirements for preventing or testing for mechanical hazards have not changed. Others have. We'll go over them now. The sharp edges test is more clearly defined in the new standard. Specifically, it references a test standard, UL 1439, which specifies how edges can be tested for hazards. This test method does not have to be used. Any device which can simulate a finger is sufficient. But UL 1439 is convenient in that it is very specific in terms of force used and the failure criteria. Now, hazardous moving parts are defined as parts which impart a 50 Newton per centimeter square contact pressure with a force of at least 150 newtons. Whenever you have hazardous moving parts, if you have not sufficiently removed all the hazards, you need to do a risk assessment to demonstrate that the hazard has been reduced as far as possible. You want to judge the hazard in terms of severity, probability, and ease of avoidance. Then you will look at all the possible means to eliminate and reduce the hazards, starting with stringent means such as barriers and enclosures, moderate means such as interlocks and emergency switches, or if the hazard is not severe, simple markings, audio-visual signals, or instructions. Third edition also defines minimum and maximum gaps to protect users from moving parts. If access to moving parts are allowed, there must be a minimum gap between moving parts to prevent crushing. If access is not allowed, there must be a maximum gap to prevent access. There are new criteria for stability in the third edition standard related to support feet or casters. They need to be rated for 4 times the normal load or tested to be sure that the product won't overbalance if a foot or caster fails. There's been a small modification to how the handle test is performed, and that is, if it is possible for a screw holding a handle to become loose, then the test is performed with that screw removed. The criteria is the same. There can be no failure or deformation of the handle. A small change has been made to the wall mounting test, and this makes for a less severe test. The wall construction that the product is mounted on during the test, if the manufacturer does not specify it, is now 12 millimeters instead of 10 millimeters. There's a new requirement in third edition for lifting devices and supporting parts. This is similar to the requirement for casters in that the load-bearing parts must be able to handle 4 times the load without breaking or deforming. When it comes to mechanical stress, there are some cases where a part of the equipment cannot withstand the normal 5-joule impact test. This is now allowable under certain conditions. Specifically, it is justifiable. The part cannot easily be touched. It is only occasionally accessed, and in this case, the part is marked with a special code. Obviously, this is not intended to be used for touchscreens or other parts of the enclosure that are frequently used. The criteria for mechanical stress testing has been somewhat expanded to include hazards associated with corrosive or harmful substances. Two things have changed in how to perform the test. The enclosure can now be empty during the test, and if an enclosure is damaged or cracked during the test, but not to the extent where the enclosure fails, a new enclosure can be used for the next impact. Now let's talk about changes to the fire hazard design requirements. 6.10.10 has requirements for eliminating or containing the spread of fire. You can eliminate the risk of fire with a limited energy circuit, or you can limit the spread with a fire enclosure and appropriately flame-rated components. Whenever you have a limited energy circuit, you do not have to meet the stringent enclosure or flammability requirements. In the 3rd edition standard, there is recognition of a very low voltage circuit, such as a 5-volt or 3.3-volt circuit, which may have substantial current but not enough to cause a fire. The standard now has created new categories for these low voltage circuits, and the current limits have been raised. For example, as seen in the first row, a 0.8-volt circuit can now have 50 amps going through it and not be considered a fire hazard. As seen in the second row, a 5-volt circuit can have up to 20 amps through it as well. For limited energy circuits which are managed by an overcurrent device such as a fuse, the allowable currents for a low voltage circuit are even higher. Going back to the 1.8 volt and 5-volt circuits again, the limit on current when a fuse is present in a 1.8-volt circuit is now 62.5 amps instead of 50 amps. And for a 5-volt circuit, the current can now be 25 amps instead of 20 amps. Now let's talk about changes to the temperature test. The 3rd edition has become more specific in how it recognizes different materials and how likely they are to burn the skin. Uncoated and coated metal are distinguished, and coated metal can be at a higher temperature, while uncoated metal has a lower temperature limit. Similarly, plastics versus glass and ceramics are distinguished. Plastics can be at a higher temperature. The requirements for glass and ceramic knobs has become more stringent, now reduced from 70 degrees C to 65 degrees C. Another change for temperature hazards takes into account that some products are meant to be in environments that are hotter than the actual temperature requirements of the standard. So the 3rd edition allows you to raise the temperature limits based on the difference between the maximum operating temperature and the 40 degrees C ambient that is assumed by the standard. So, for example, if you have a product that is used in a 65-degree ambient, a plastic enclosure can now be 110 degrees instead of the 85 degrees required by the standard for parts in a 40-degree ambient. This is a fairly significant change for products that are meant to be in high-temperature environments. Here are some other changes. Another addition to the standard prohibits exposure of toxics. Here, there are aggressive substances that can be spilt during product operation, The surfaces must be compatible with that substance. For example, you cannot have a metal enclosure surface that would corrode when using an acid in your product because it would compromise the integrity of the enclosure. One of the relaxations of the standard is the new fluid pressure exception. For Europe, the hydraulic test of pressurizing a vessel to determine if it leaks or bursts is now optional, based on whether leaking or bursting would cause a hazard. For example, if the leaking or bursting liquid would be well contained within the enclosure and could not wet any live parts, the test would not be required. The test criteria have also been simplified. Instead of the second edition sliding graph for calculating the test pressure, it is simply 1.5 times the rated pressure for leakage and 2 times the rated pressure for bursting. Annex G for North America, which is more stringent than Clause 11, is now optional if pressure is below 50 kilopascals or the pressure-volume combination is less than 200 kilopascal liters. There's now a distinction in the standard between products that are meant to emit ionizing radiation and those that are not. Products that are intended to emit radiation do not have the severe limit. Instead, if they exceed 5 microsieverts per hour, they simply have to be well labeled. However, if the product is not intended to emit radiation, the second edition limit of 1 microsievert per hour still holds. Similarly, the standard now acknowledges that some products will exceed the ultrasonic pressure limit of 110 decibels and simply require them to be marked. There are a few changes to the component requirements that I want to make note of. The first is that a product that is compliant to a standard other than 61010 may not be sufficient. For example, you may have a 6950 power supply that is meant for a 2,000 meter environment, but needs to go into a product at high altitudes. This power supply would need further investigation. Similarly, a listed power supply would still need to be tested for dielectric strength after humidity. Now, on the other hand, motors and transformers do not have to meet component recognition if they can meet the requirements of 61010-1. Last, printed circuit boards no longer have to meet V-1 flammability ratings if they have limited energy circuits on them, such as the 5-volt 20-amp circuit that I discussed earlier. There is a small change to the interlock standard which can be significant in terms of design. It requires that an interlock cannot be defeated without either removing the hazard or using a tool. The Clause 16 is a new clause for ergonomics and reasonably foreseeable misuse. Ergonomics, or human factors design, is meant to prevent injury to users based on their capabilities and limitations. It is important, for example, that users of all sizes be able to access emergency controls, view and understand emergency indicators and displays, and reach all terminals. Another new term is reasonably foreseeable misuse. In the previous edition, it was sufficient to have a clause in your manual stating that if a product was used outside of its normal operation, then the protection provided by the equipment may be impaired. With the third edition standard, the manufacturer must consider the possibility that a product will be misused and design safety features to address this possibility. The final change in 6.10.10 third edition is the addition of a new clause and new concept, the risk assessment. Risk assessment is meant to cover hazards that may arise from technological aspects of a product that are not already covered in the standard, but which may cause harm. It should also always be used whenever there are hazardous moving parts or radiation exposure hazards. Risk assessment is an iterative process because a particular measure of risk reduction may not lower the hazard to a tolerable level. If not, you need to look at other means of reducing the risk of hazard. Here are the 4 steps. Analysis is where you identify the risks. Evaluation is where you quantify them. Reduction is the design measure to reduce the risk. And iteration is the reevaluation of the risk to determine if additional steps are needed. In order to come up with as comprehensive a list of hazards as possible, it is important to identify not only the users, but anyone who might come in contact with a product, especially a product used in the home. Next, there is use and misuse. At every stage of use, there is the possibility that someone will make a mistake or use the product in a way that was not intended. These misuses or abuses must be taken into account in the assessment and looked at every stage of the product's life cycle and usage. For each hazard that is identified, the risk must be quantified, first in terms of severity. Can it cause a fatality? Could it shut down a building? Could it contaminate the environment? Or, on the other hand, would it just require some first aid? After you determine severity, you determine likelihood. Will it happen frequently several times a year, or probably never, or once in the lifetime of the product? Once you've quantified the risk in terms of severity and likelihood, you can assign to it a risk category. The goal is for all the hazards to be tolerable. If not, something more must be done with the product. There are 3 basic ways of reducing risk. The most effective is to have a change to the design, but in most cases, if you could have, you would have. For example, you cannot eliminate a cutting tool. You may not be able to eliminate radiation, but you can shield it from your user. This can be an enclosure, a barrier, an interlock. It can be an emergency stop, which might limit severity even if it doesn't reduce the hazard or eliminate the hazard. The last and least effective means is by educating your user. The best way might be an alarm. Next is a warning label. Training may be an option. Protective equipment may be an option. Information in a manual is one of the least effective means of reducing risk. Sometimes it is the only option. When the likelihood is frequent but the severity is minor, informing the customer may be sufficient. That's for you to decide. The last step of the risk assessment process is to redetermine the risk. Has the means of reducing the risk put it in the tolerable category? If not, you need to look at what else you can do. As product safety engineers, our role in reviewing the risk assessment is to review your process, see if we come to the same conclusion that you have in terms of making the product as safe as possible, and we may design fault tests to simulate the hazards and verify that they are a tolerable risk. And that's the end of my presentation. Please let me know if you have any questions.
Great. Thank you, Lauren. That concludes the presentation portion of this webinar. Tomorrow, an archived copy of the webinar will be available on metlabs.com. We will send a follow-up email with a link to this file. Now we will answer questions. If you have a question, please type it in the questions area of your control panel. For questions we can easily address now, we will read the question aloud, then give the answer. Give us just a minute to get organized. And joining us here to answer questions is Rick Cooper, who is the director of MET's Product Safety Laboratory.
Rick?
Yes, I'm here.
Can you tackle this where to get third edition question?
Oh, where to get the a copy of the standard? Sure. Well, we use IHS, specifically global.ihs.com. I believe I saw that the question included a comment they could not find it at ul.com, but I have checked. It is available at ul.com. If need be, we can send a direct link if that would help. But, it should be available at IHS or at UL. The UL version. The international version should also be available at IHS.
I'll take the next one. This is a question that says, is 61010-1 a mandatory requirement, just like the EMC directive for 2004-108 EC? This is a mandatory directive as part of the technical file that is expected. And additionally, as I said at the beginning of the slide, as of October 2013, if you were previously certified to 61010-1 second edition, you must convert to third edition. Rick, can you talk about ATEX?
I can say this much. Unfortunately, this was not an ATEX presentation, so I'm not going to have much information to share. However, the question was, is there any impact on ATEX? And really the only impact on ATEX, for those that may not be familiar, is the European Directive for Products for Use in Explosive Atmospheres. That's going to require that electrical products comply with ordinary location requirements or ordinary directives, such as the low voltage directive or other directives. And when those directives call out specific standards such as EN 61010-1 and third edition, then it would be necessary to comply with that edition in addition to obtaining compliance or demonstrating compliance to the ATEX directive. And that's about all I could say to that right now.
Okay. Mr. Grimes, you might want to clarify your question, but I will try and cover it. In terms of the extent of coverage, 61010 is made for a final product as opposed to a component. So when you talk about transducers, for example, that's at the component level, and while there are certain requirements for pressure or temperature within the 61010 standard, it is more meant for a product that is using the transducer as opposed to the transducer itself. Rick, do you have any further comments on that?
No, I do not.
Okay. The next question was, when is the real EU date of withdrawal on the second edition? That is October 1st, 2013. Now there's another question about, hold on a minute. The status of the UL version of 61010-1. For UL, you can use either second edition or third edition. However, as of 2018, or specifically January 1st, 2018, second edition will be withdrawn. At that point, anything that's still certified to second edition becomes obsolete and has to be converted. But again, this is 5 years from now. Somebody asked a question about the test voltages for IEC and UL 61010 and how they are different. And I think I'd like somebody to clarify where in the standard you're looking. I know for a fact that the test voltages for low voltage are different, but I'd have to investigate a bit more to see the national difference for 61010 UL versus IEC. Rick, do you have any comments about that?
I was just going to add to that, Lauren. The national differences, of course, would be pointed out within the individual standards. So if it's a U.S. national difference, it would be in UL 61010-1 third edition. And if it's different from the main standard, which is IEC 61010-1 third edition, then there should be some sort of an indicator with that table or the clause that's affected. That's pretty common. I've not seen that missed yet. But Lauren, you would have to get the information you've requested to look into that a little bit further. And then the only other thing I could add to that is, besides there being a UL 61010 third edition standard, there may in fact also be a separate document that just covers the national differences, basically those requirements that are different from the IEC version of the standard. Sometimes there's one or both of those documents available. As far as how this is addressed at MET, if the standard has a different requirement, we're going to require each requirement or the more stringent of the two. It's just pretty as basic as that.